Okay, so let's go over experiment 6. Quickly over the experiment and then some of the calculations. Okay, so in this experiment you had a saturated solution of calcium hydroxide. It's been sitting overnight. As you notice, you have some white powder on the bottom, which is calcium hydroxide. And then we assume that equilibrium has taken place and that we have a saturated solution of calcium, 2 plus and OH minus. Okay, so you were asked to obtain approximately 70 milliliters of that solution, and hopefully you got a solution that was clear and colorless. If it's not clear and colorless, you might want to think what effect that might have on your calculations. And then you took 10 milliliters of this solution and placed it into an Erlenmeyer flask. And then you added an indicator. In case you added bromo-cresol purple indicator. And if the pH is greater than 6.8, the color will be purple. You might want to think why the color is purple in terms of your Chem 1300 knowledge. It's not really important for this lab, it's just interesting. And then you did the titration, and of course it's purple because we have hydroxide in solution, right? The pH is greater than 6.8, it's a basic solution. Then you did the titration, and you hopefully got a yellow endpoint. And you did the titration with hydrochloric acid, so of course the pH is going to be acidic at the endpoint, so it's a yellow color. And then you took another 10 milliliters and you were going to do a titration this time with EDTA. And so the first step was to add a few drops, I think it says 5 drops of this Calmagite indicator, and this will bind to some of the calcium in solution. And then you did a titration from your burette with EDTA, and this has a higher equilibrium binds to calcium than does this one, so it will replace any of that. And so initially it's a red color when it's bound to calcium, and then once this is free from calcium, it will have a different color, the blue color shown here. Okay, and that will be the end point of the titration. Okay, let's do some of the calculations that you're going to have to do for this lab. So for the HCl titration, the HCl titration of hydroxide. Okay, and I'm going to make up some numbers, and so you just got to be careful. Make sure you use the numbers that you recorded in during your experiment. So you had a burette, and this is very crooked, but it's just for illustration. And in that burette, you placed, and I got these numbers from the lab for here. Your concentration of HCl in the burette was 0.01486. Okay, and then you had the Erlenmeyer flask. Inside that Erlenmeyer flask, you had 10 milliliters. So there you had 10 milliliters, okay, of your calcium hydroxide solution, so CaOH solution, okay, and hopefully it was clear. Okay, that'll make might be better for your results. You might want to think what the difference might be if it wasn't clear and colorless and it still had some of the calcium hydroxide solid floating in it. Okay, so let's imagine you took, let's say when you did the titration, you're adding the HCl to the solution. Let's say you got 20 milliliters was the end point. Okay, so 20 milliliters. Okay, in these calculations, I'm not worrying about significant figures. That's your job to do in your report, to think about that. So let's say we had approximately 20 milliliters. Well, that is equal to 0.02 liters. I know the concentration here. This is molarity. Okay, so if I multiply the volume that I added by 0.01486 moles per liter. Okay, liters of course will cancel, okay, and I will get the moles of HCl added. And so if I do this calculation, I did it on a piece of paper, and I get, according to my numbers, 2.9 0.72 times 10 to the minus 4, okay, and that's moles of HCl. Okay. Well, from this we can determine how much hydroxide we had. Okay, so we know that 1 mole of HCl will react with 1 mole of hydroxide. So this will also be equal to the moles of hydroxide. Okay, so this is also equal to the mole, okay, of OH minus. Okay. We calculate the concentration of hydroxide. Okay, so the concentration of hydroxide, okay, OH minus in this solution here. We just divide the number of moles that we calculated, so it's 2.972 times 10 to the negative 4 moles. Okay. And that was in 10 milliliters, so that's 0.01 liters. Okay, and I get, what did I get? I got 0.0297 moles per liter. Okay. And so how do we determine what the concentration of calcium is? Well, we know that calcium hydroxide, that's supposed to be a 2, calcium hydroxide, okay, dissociates into calcium 2 plus, okay, plus 2 hydroxide, 2 OH minus. Okay. So if the concentration of hydroxide is 0.0297, okay, well then we have half as much calcium 2 plus, so we just divide this by 2. Okay, so we go 0.02972, and we divide that by 2. Okay, and that will give us the molarity of calcium 2 plus. Oops, calcium. It's not in the show yet. So the molarity of calcium 2 plus. Okay, we got the molarity of calcium 2 plus, and we got the molarity of hydroxide. Okay, so you also want to determine a KSP value. So KSP, okay, KSP is going to be equal to calcium 2 plus concentration times the hydroxide concentration. Okay, we learned this stuff in the lectures already, raised to the power of 2, OH minus, raised to the power of 2. Okay, and so we know the calcium concentration is this number here that we divided by 2, and this number here, and then we get the KSP value. Okay, just plug in the calcium concentration, the hydroxide concentration, do the arithmetic, and out will come a KSP value. Okay, so with my numbers, you can try with my numbers. I got a KSP value of, in this case, 1.3 times 10 to the negative 5. Okay, and of course I'm using fictitious numbers. Okay, 1.3 times 10 to the negative 5. Okay, so that was the HCl titration of hydroxide. So let's take a look at the EDTA titration. So the EDTA titration, okay. And this time we were titrating calcium, right, of calcium 2 plus in this case. Okay, so again we had a burette, okay, that was filled with EDTA solution, and the concentration of EDTA okay, is equal to 0.007 moles per liter. Okay, and you had a Erlenmeyer flask, And in that earthenware flask, you had 10 milliliters, okay, or you had 0.01 liter of calcium hydroxide solution, okay, calcium hydroxide solution, okay, and you perform the titration, you reach the endpoint. So let's say again you determine the endpoint required 20 milliliters of the EDTA solution, 20 milliliters. Okay, so how do we calculate the concentration of or the moles of EDTA that was added? Well, 20 milliliters, that's 0.02 liters. We times that by the concentration, which is 0.007 moles per liter. Okay. So in this case, we end up with the moles of EDTA being 1.4 times 10 to the negative 4 moles. Okay, that's moles of EDTA. Okay. Well, if you read your lab manual and you take a look at it, we know that 1 mole for every 1 EDTA, so 1 EDTA molecule, okay, is going to complex, okay, or bond with 1 calcium ion. Okay, so this directly gives us the concentration or the number of moles of calcium. So this is also equal to the moles of calcium 2 plus. Okay, so to get the concentration of calcium 2 plus, okay, calcium 2 plus, that's going to be equal to the moles, which is 1.4 times 10 to the negative 4 moles, okay, divided by, and again we had 10 milliliters, so we had 0.01 liters, okay, and I get a concentration of 0.014 moles per liter of calcium 2 plus. Okay. Okay. Well, what is the concentration of hydroxide? Well, again, we have our equation: calcium hydroxide, okay, solid. Okay. We get calcium 2 plus 2 hydroxides when this dissociates. 2 hydroxides. So if the calcium concentration is 0.014 molar, what would this concentration be? We need twice that, right? So the hydroxide concentration is going to be equal to 0.028 molar for the hydroxide. Okay, and so now to calculate KSP, use the same thing we did before with the HCl titration. We have KSP is equal to the calcium 2 plus concentration times hydroxide raised to the power of 2. Okay. So we plug in our calcium concentration, we plug in our hydroxide concentration that we determined, and we get a KSP value. And in my case, based on my fictitious numbers, I determined a KSP of 1.1 times 10 to the negative 5. So that's all for the calculations. And so you want to think about comparing the concentrations of the calcium and the hydroxide as determined via EDTA versus HCl. You also want to determine the KSP values determined via EDTA and HCl. And you also want to look at a literature value with the literature value for the KSP that's well known for calcium hydroxide, and consider why your value might be the same or different than that value.